something malicious. So these are, that's another problem that I think will get more attention in the future. There's a lot of timing-based attacks where, say for instance, you're wgetting a file from the server, and it subsequently gets another file on that server, and the JavaScript itself says, there's a 2-second period between each request. If you request it at 1 second period, the server can deny your request. The client can also use timing within the JavaScript so that if you don't respect the timing loops, then it will decode incorrectly. And finally, they can introduce infinite loops so that it never finishes evaluating in the case that it detects an incorrect version. Or these are ways to prevent us from finding what's actually there. So the final technique of preventing detection is actually using browser plugins and other techniques that can be used to load JavaScript. In the case of SWF files, they actually pass it back to the browser, and the browser will execute the JavaScript. In the case of PDF files, it contains its own JavaScript engine, which Adobe has released on the second link there. So a lot of improved obfuscation PDF files this year that I've seen also. We've talked about what the attacker's goal is. We're going to talk about what's available to a defender. So you could open the script in a browser, modify it, replace things, and print out the contents of the decoded what would be decoded. This is really not an effective technique anymore because too many scripts are using basically checks against the content. So you could take an MD5 sum of the content, compare it against a predefined value, and then determine if it has been modified. So you can get around this by using either an actual interpreter, which is SpiderMonkey, or using various debuggers, which execute in the context of the browser. So you don't actually modify the scripts. So this is kind of important to do. And then finally, you could also, there's several projects that have modified the JavaScript engine itself to extract information and variables. So these are some implementations similar to JSONPack, and they're slightly different in that my main goal is to make it quick and also to make it very lightweight. In the case of WebAwet, it actually uses a real browser, and that wouldn't be effective if you're trying to do it against every URL on a corporate network. So definitely check these out. So here are a variety of different types of decoding techniques that you could take. In the case of very simple scripts, you could just write your own decoder, translate, and figure that out that way. But once you get to the dynamic versions of those, they use the environment variables, they use HTML, they use the PDF format, a variety of these different things. So, and then finally, the most difficult, using server-side defenses and determining the versions you're running, and tracking your IP address. Basically, in the most difficult case, the best thing for you to do is actually visit it in a virtual machine, or visit it like an actual user would. So there's really two different solutions here. You could go after the full environment, put all of your tools to hook the browser, or you could do it strictly on the network side and watch passively as these scripts go by, so that you don't have to worry about these detection and difficult problems. So the source code is based upon SpiderMonkey and Python. The Python controls the SpiderMonkey program, which is the JavaScript interpreter. And this is the source code that I've basically released, and it basically has a JavaScript part which defines the environment. It setups all the hooks, and there's also a file which does the post-processing and part of the detection. What this does is, after the script executes, it will look through the current defined variables and look for shellcode and URLs that were defined in any variables. And the Python part of this is the detection library based upon Yara signatures, and also PDF, SWF, JavaScript decoding, and the main engine itself. So the first main new feature is the network decoding. You can pass either a network interface or a PCAP file, and the preferred technique is a PCAP file because you don't have to run as root, and I think a lot of the benefit of the active mode is you can fetch any decoded URLs. And for instance, if it was shellcode and your actual browser didn't download the shellcode because it wasn't vulnerable, then this will go and download the shellcode or any other discovered URLs. So in that case, you can get the best of both worlds. You can also process scripts or files that you have locally with this. So a couple challenges I tried to solve when using the network version. Fragmentation with IP packets, and also TCP reassembly, and pipeline request, where there's multiple get or post requests in the same packet or in the same stream. And additionally, processing of gzip and chunked encoding. I didn't do anything for SSL. And then after we extract all these streams, we still have to do the JavaScript decoding. So the pre.js file is largely responsible for this. And additionally, you could, I do recommend modifying SpiderMonkey to take advantage of an eval hook. So to enumerate the environment of a real browser or the PDF engine, I use everything is treated as an object, so you can go through every every variable of that enumerated variable of that object using this type of loop, and then print out that information whenever you need it. So in this way, we can try and recreate the browser's environment as realistically as possible. And then in JavaScript, you can reassign the variables for functions. So if we take a variable function name and set it to our, we take a copy of it, then define it as a new function to execute the old function and do additional work, such as print out the contents of the obfuscated code, then we can get what we need. So there have been a lot of new hooked functions that are necessary to decode these things, and several of them are time-based. So set interval is one that I'll have an example with later. And additionally, you can do this with PDFs. Dieter Stevens has created a tool where you can just pass a file on the command line and insert JavaScript into a PDF file. And then you can profile it this way and figure out what's defined in the current environment and what they contain. So the other feature of JS Unpack is the rules language. This processes all decoded content. So if a hook applies to something, then we can define a rule that looks for any of the decoded data. In this case, this is a newer media.newPlayer vulnerability for PDF files. And there's, at the top of this Yara rule in bold, you'll see decoded PDF, and there's another keyword called decoded only. This is the rule language, which basically does what it says and allows you to put filters on the rule to say that this only applies to decoded content and not to regular HTML. So there's another type of rule that is necessary to detect these things, and that's a dynamic rule. And this is JavaScript. And basically, we're creating the object which will execute once the JavaScript actually executes. So both of these are necessary because if our script contains an error, we still want to process the static content and run the Yara rule. But if the Yara rule, if the attacker assigns the media to a variable, then our static rule will never detect it. So there's an output directory with JS Unpack, and it creates various types of files. Whenever it decodes something, it'll create it according to that name. In the post-processing, when it decodes shellcode, it'll create it of that name. And with the -s option, you can save all the streams and the dgzipped and dechunked content, and those get saved as separate names. Whenever the shellcode matches a URL within the packet capture, that's a special case where you know that the client who downloaded it was actually exploited successfully. So in that case, you can determine, you have a real incident here. Malicious code was installed. And then there's various other debugging and files of that type. So by default, it only outputs malicious content. If you want to see everything, you would use the -v option, or if you want to see the errors and additional information, use the capital -V. There's a graph mode showing the path, and this shows circled by red boxes whenever something is detected as malicious or suspicious by the rules. And this gives you some idea of the data structures that I've used. They contain a link type so that we can determine what type of detection we want to do on them. So one of the challenges I've tried to overcome with this is, of course, the infinite loops. So I put time limits on the script evaluations, and whenever it exceeds that limit, then I throw a warning. And in my experience, most of the malicious scripts are the ones that take longer. So the benign scripts typically are very quick to evaluate. There should be very few exceptions to that because they're generally assigning large amounts of data and doing heap spraying so that when the exploit is successful, it can jump to that address. But in those cases where it times out, we may not get the full decoding because it's based upon the machine being able to do that quick enough. And some of these exploits take, a minute or two to actually exploit a victim. The other thing that a lot of attackers are doing is profiling the user before they do things. And we can run every case of every version within this environment and determine which decodings belong to which version. So I'll show you an example, but these are the versions I'm currently using. And what happens is it'll evaluate the first one, and to save evaluation time, it will only evaluate the next ones if that first one didn't take too long. So basically, this is an effort to prevent it from taking several minutes to evaluate something. So this is an example of a PDF that I've included in my source code as an example. And this is a malicious file where the JavaScript uses a time-based decoding, and the set interval function basically says after 1,000 milliseconds, I want to set this variable to be X, where if it doesn't evaluate, it's still G. So the exploit here uses the annotate PDF field, and if it does evaluate, then it'll translate the get annotates function into the xet annotates function. So the problem here is we define this app.setInterval, and if you evaluate it immediately, then this will not decode correctly because it's this xet annotates function is not a valid function. So to handle this, I try to determine whether to process the hook within the immediately or within the post-processing. And if it's a larger value that the time will take, then we delay it and we still execute it. But in this way, we can prevent it from doing these anti-decoding techniques. So this is a case of version detection. Basically, we see that if you set the PDF version to be version 7 or empty, we don't get any decoding. So it's not targeting those versions. If you target version 8, you get 234 bytes, and version 9, you get 144 bytes. So in this case, I choose to take the largest decoding. We could also process those other paths, but again, in an effort to reduce our time, we're not. So yeah, this is a Russian exploit kit, Zopac. And basically, to summarize, we have a lot of dynamic content that we can process. The HTML could contain get elements by ID and use the various things that are contained within the HTML. And to handle that, we have to process the HTML correctly and define the JavaScript environment dynamically based upon that HTML. I've also seen a lot of attackers using last modified and some of the HTTP headers that are available to scripts. So we have to process those. The PDF decoding, there's a lot of filters that I'm trying to implement and add to this file. And finally, the SWF triggers have to be interpreted to get the full picture. So how does this apply to intrusion detection? Right now, it's very dependent upon PCAPs. Even though you can run it on a network interface, I don't recommend it because it's running as root, and I haven't performed a lot of testing on that particular feature. Right now, it's using libnids, which is a fairly well-tested library for intrusion detection. Once Snort and other IDS engines like Suricata can support this type of decoding, I think they're going to need multiple CPUs, and they might even require offloading the content or offloading the decoding, because the memory requirements for this type of thing are extreme, and it could affect other processes on the system. But I would like to add it to intrusion detection systems. Regarding inline mode and actually blocking the content before it hits the victim, I don't think it's practical to do that, but perhaps further testing would reveal that the benign URLs are actually going to be very fast in that case, and malicious ones are not. So it might be possible, but not likely. I think in the short term, probably a learning blacklist and just using it in a passive mode would be more effective. So I also have updated the web interface so that if you want to just use this without actually installing anything, there are a number of libraries that you have to install, libnids, several Python libraries, the Yara detection library. So if you just want to use it, and you can just upload PCAPS files or URLs to my site. This is an example output showing the detection on a URL that was submitted. And I've decided to make all of my data very public. So in this case, you can download the zip file containing all of the logs, all of the decodings, and anything that this submission has created. I also added on the submission page a checkbox allowing you to submit things as private, because a lot of people have told me that they can't, they don't want it to be public. It could have a bad impact on their business. So a lot of what needs to happen is the rules themselves could be custom to your organization or whatever you want to detect. This is the RSS feeds that I've created from all my data, and you can subscribe to any of these and see which exploits are being detected whenever an exploit is detected. So yeah, I think this will be useful for tracking new vulnerabilities too. I plan on creating cases where we can determine that multiple decodings have occurred, but we don't detect anything, and fix those cases. So, any questions? Yes?
For the pre-cooking or the rules, is there any way to do some basic heuristical stack analysis? So in one case you said on the slide, you have an infinite loop while one, do blah. And so if you do some type of heuristical analysis, you kind of gather that maybe I should be using this particular version. Is there any way to do that in your rules currently?
So that's a very difficult problem. I tend to not want to modify the scripts.
Well, not so much modify
yeah.
it, but just jump. Okay, because you're not going to be able to execute some idioms. So what you do is you just kind of say, oh, well, this says while one. I know this is an infinite idiom. I'm just going to jump past that or jump out of that loop.
It might be possible. I haven't looked into it yet, but that's a good point. Yes?
A lot of the malware I'm seeing is being downloaded through HTTPS. So what are your thoughts on really how to handle, SSL, protected malware?
I haven't seen that many through SSL, but I think that definitely this tool would not be the ideal, because unless you set up a global SSL proxy and tried to, have a visible part of that, it's not going to happen usually. So I think what needs to happen is the browser engine. I don't know if you're aware of the Adobe solution to this problem, but in their corporate version, you can specify functions you want to disable. So I think the equivalent thing has to happen for the browser, so that you can define, I want to disable these functions, and the browser will never execute them. So that's more a protective measure, but in terms of detecting, I think that's not something I'm going to be able to do.
What if you integrated it with like a proxy like Fiddler or Burp or something like that?
Definitely, yeah.
Could you repeat that last question?
So the question was, basically, would what would you do in the case of SSL? And if SSL websites are delivering exploits, basically. So how would you decode that? Yes?
You talked briefly about fragmentation. Are you talking about just the general fragmentation of large files, or are you seeing kind of active fragmentation to deploy a lot?
So I think there are like IP fragmentation and file fragmentation, and I think in the future it will evolve into Web 2.0 fragmentation, which makes the dynamic requests, and the server could also use timing. So I think that's the future. We can hook those things and fetch them, but it's still a difficult challenge if you're not in a live environment.
Put any thought into doing this client side, like as a plug into a browser or
So
client?
there are client-side tools that are acting more like debuggers, and I think that's the better solution. I don't know how I would, perhaps recompiling SpiderMonkey within Firefox to do this. Those types of things could be effective, but definitely that's not my main goal. It's more, how can we do this on an internet pipe? Yes?
Did you perform any performance matrix on each script? So CPU versus how many clients can connect, and how many streams you can scan with your plugin?
So I don't have a good answer for that. I have performed testing against a large volume of sites, but just taking the average times that it took to process those is what I based my evaluation times on. So I think that's where I came up with the fact that non-malicious scripts don't frequently take a lot of time. But I don't have a better answer than that. All right. All right, thanks, everyone.